As Bodhi indicated, we will talk about bond and development length today. I have to confess that I am a bit unsure of myself this morning. The topic is an involved one, and I know a bit too much material that does not really fit into the 2.5 hours we have. So, and I didn't find obvious places where to cut. So I will get into the material and see how it goes. There is a possibility that I may go beyond the 2.5 hours. I will try not to, but if I have to, please bear with me. So as I did yesterday with Shear, I think it is good to start with the very basics. So in the picture on the screen, this is I'm sorry, I cannot push. So this is a beam before it is loaded, and obviously the concrete and the reinforcement are together. When it is loaded, if there is no bond between the concrete and the reinforcement, then there will be slip between the concrete and the steel, as clearly shown in the picture. So the reason why in a typical reinforced concrete beam, the concrete and the reinforcement deform together is the bond stresses between the concrete and the steel. Bond stresses acting on the concrete are shown in the picture. They are trying to bring the beam in towards the central load, and that's what the arrows indicate. This direction of the bond stresses is important. Equal and opposite bond stresses act on the reinforcement. Those stresses are trying to stretch the reinforcement, trying to bring it out. So the bond stresses acting on the concrete are trying to bring the concrete portion in. The bond stresses acting on the reinforcing steel are trying to bring the reinforced steel outwards, and the two together would make the concrete and the steel deform together under vertical loads. So this is the very basics of bond stresses between the two. Now, if the bond between steel and concrete completely fails, and if there are no hooks as shown in the picture, the beam will fail suddenly. The reinforcing bar will slip out, maybe not all the way out, but it will slip, and then the beam is like a plain concrete beam. One of the cracks you see will go through, and that will be the end of the beam. However, if you hook the ends of the bar, then the beam does not have to fail when bond fails, because the beam then will or can act as a tied arch. This is the shaded portions are concrete in compression, and so that forms an arch inside the beam. The reinforcing bar, if it is hooked, can act as a tension tie, and now it is a tied arch that can go on carrying loads. So the failure of bond does not have to be the failure of the beam if the bars are anchored, as we call it, or in this case, the anchoring is through the hooks. Okay, as we did yesterday, we are taking a small portion of a beam, two sections that are distance dx apart. The tension in the steel at the left section is T. On the right section, it is D plus dt because the bending moment is a little bit different on the right section. The compression in the concrete on the left face is C, on the right face is C plus a differential C. The shear is V on both faces. They have to be equal for vertical equilibrium. And the lever arm between the concrete and the tension, the compression and the tension forces is JD. In the days of working stress design, we used to use that notation for lever arm, JD. Now, the reinforcement, which is subject to T on the left face and T plus dt on the right face, maintains equilibrium because of these bond stresses that have developed. The bond stresses multiplied by the perimeter of the bar or bars will have to be equal to the dt for horizontal equilibrium. Okay? So forces and stresses acting on elemental length of beam. In figure A, we have the free body sketch of reinforced concrete element. Figure B, the figure below, I have the free body sketch of the steel element. And the free body sketch of the steel element involves the bond stresses U. Okay? The same picture, but now we will look at a few things. So dt, the incremental tension in the reinforcement, is the incremental moment between the two sections, the left and the right, divided by the lever arm. Okay? Tension is equal to moment divided by lever arm. So this is an understandable relationship. The dt, the incremental tension, is the bond stress U times the total perimeter of all the bars. That's what sigma sub 0 indicates, sum of the perimeters of all the bars, okay, times dx. So dx is the length, the sigma sub 0 is the total perimeter. So sigma sub 0 times dx is the total area over which the bond stress acts. If we multiply sigma sub 0 dx by u, we find the total bond force that has to equal the incremental tension dt. Okay, so this equation is actually the equation of horizontal equilibrium for the free body diagram at the bottom. U is the local average bond stress per unit of bar surface area. Everything that is said needs to be said per unit of bar surface area. And the sigma sub 0 is sum of perimeters of all the bars, as I've indicated. Okay? So U then is dt divided by so the U is dt over sigma sub 0 dx. Okay, now dt is dm over jd. So if we combine the two equations together, u comes to dm over dx omega sub 0 jd. This is from the two equations. I don't know that I need to go into any more details. Very straightforward. So then U comes out to dm dx is B. Remember from yesterday, shear is the differential of moment. So U is V divided by the sigma sub 0 and the lever arm JD. This is the conventional elastic crack section equation. In the days of working stress design, everybody was familiar with this expression. Okay, it's a long time ago. So lowercase u, the bond stress is the shear divided by the sigma sub 0, the total perimeter of the bars, and JD, the lever arm. This equation applies to tension bars, not to compression bars. That should be obvious. Okay. Now, so variation of steel force and bond stress in reinforced concrete members subject to pure bending. That's what we are looking at in this picture. Variation of steel force and bond stress in reinforced concrete members subject to pure bending. The first picture shows you a cracked concrete segment. So it's a segment of the beam where we have two flexural cracks, and the bond stresses are shown. So between the cracks, the direction of the bond stresses are can be seen. Those directions are important to understand, and outside of the cracks also the directions. So the so figure B has bond stresses acting on the reinforcing bars. Figure C, very importantly, shows you the variation of tensile force in the steel, okay, where the concrete cracks, the concrete does not carry any tension. So the tension in the reinforcement goes up. In between the cracks, concrete still carries some tension. So the steel tension goes down. And again, at the next crack, the steel tension picks up. So the tension in the reinforcing steel is not constant. It varies between cracks as shown in the picture. And then the bond stress U, which is proportional to dt dx. So bond stress U is proportional to dm dx, which is the same as dt dx. Okay, so as the tension varies, the bond stress varies, and so where the rate of change of tension is the highest, the bond stress is the highest. Typically, we have the highest bond stresses close to the tension cracks. So here it is high, here it is high, here it is high. So these pictures are not only realistic, these are basically representation of test results. So the way you see it is the way beams behave. Okay. So cracks, the bond stresses acting on the reinforcement, the variation of tension along the reinforcement in the beam. The tension is the highest at the cracks, lowest between the cracks, and because the tension varies, the bond stresses vary as shown in the last picture. Now, the effect of flexural cracks on bond stresses in beams. So now this was a beam segment. Here you are looking at, this can also be called a beam segment, but this is half the beam. Okay, so this is the support, this is the loading. The bending moment diagram is here. So if you divide the bending moment by the lever arm, you have tension in the reinforcement. So theoretically, the tension in the reinforcement follows the dotted line. But because of the cracks opening up, The actual tension in the reinforcement varies as shown by the solid line. Okay, again, at the cracks, concrete doesn't carry any tension, so the entire tension has to be carried by reinforcement. In between cracks, halfway between the cracks, concrete carries the most tension, so the reinforcing steel carries the least tension. So the tension in the reinforcement varies as shown in the picture. And since there is a variation in tension, there is a variation in bond stresses. Okay, so this is a crack. Close to the crack, we have the highest bond stress in one direction. After the crack, it is highest bond stress in the other direction, and so forth. Okay, so and these directions are important. At the, as I pointed out, at the crack, the direction of the bond stress changes. Okay, so so this is the variation of bond stresses along the uh, the left half of the beam in the picture. So picture A shows you beam with flexural cracks. B shows you variation of tensile force T in steel along the span of the beam. C shows you variation of bond stress along the span. Okay? Now, because of everything that we discussed, okay, if the bond stresses become too high, then there is failure of bond, which will show in the form of splitting of concrete along reinforcement. Okay? Splitting can be in the vertical plane. Splitting can also be on the horizontal plane. Splitting quite often starts at the diagonal crack and then proceeds to the end. That is pretty usual. So splitting of concrete along reinforcement, the bond stress U times the perimeter gives you the bond force per unit length of bar, and that is indicated by capital U. Okay, lowercase u is a bond stress, capital U is bond force per unit length of bar. Ultimate average bond force per unit length of bar is approximately U sub n equal to 2.9 square root of f sub c prime in SI units. That has been observed by very extensive testing at the University of Texas and elsewhere. So when the average bond force per unit length reaches that value, we are likely to observe splitting of the concrete as shown in the two pictures. Splitting can be in the vertical plane or the horizontal plane. Bond forces of above magnitude, this 2.9 square root of f sub c prime per unit length, result in failure by splitting, in large and excessive slip, or in other prohibitive deformations. For several bars in one layer, instead of the one bar as in the last picture, for several bars in one layer, at typical spacing found in beams, the ultimate bond force is about 80% of above. So closely spaced reinforcement, we have to, the splitting can start at 80% of this value of 2.9 square root of f sub c prime. This is all very, very important stuff, and the basis always is experimentation, pretty thorough, systematic investigation. Okay, now it is a full beam between simple supports. The loading is 2-point loading. Those are kind of immaterial. What we are going to discuss will hold irrespective of the structural member. In any case, this is a a simple case that makes the presentation easier. Okay, so steel stress is zero at the supports. There is no bending moment. There is stress. There is no stress in the reinforcement. So F sub S at, so it is zero at the support, and in this section A, the steel stress is F sub S. We just denote it by F sub S, whatever it is. Average bond stress per unit length over this length L is the cross-sectional area of the bar times the tension stress in the bar. A sub B F sub S is the force in the bar, divided by the length. Okay, average bond stress per unit length over this L is A sub B F sub S divided by L. The other way to think is the stress in the bar changes from 0 to F sub S because of bond between the reinforcement and the concrete. Okay? So this bond stress U or bond per unit length U multiplied by L must have added up to A sub B times F sub S. Okay? So that is understandable. Minimum length necessary to develop by bond bar force A sub B F sub S is A sub B F sub S divided by the ultimate value we saw on the previous picture, the 2.9 square root of F sub C prime. Okay, if that is the ultimate bond per unit length, then minimum length necessary to develop by bond this force is A sub B F sub S divided by the same U sub N. Minimum length necessary to develop the full yield strength of the bar, A sub B times F sub Y. Now we are not developing F sub S, we are developing yield strength F sub Y. The minimum length necessary to do that would be A sub B F sub Y divided by 2.9 square root of F sub C prime. 1 divided by 2.9 is 345. So that gives us the expression for what we call development length, 345 A sub B F sub Y divided by square root of F sub C prime. For bars at the relatively close spacing typical of beams, the L sub D, which is A sub B F sub Y over the U sub N, which for a single bar is 2.9 square root of F sub C prime. Remember, if we have closely spaced bars, this U sub N is 80% of 2.9 square root of F sub C prime. So the required development length goes up by 1 divided by 0.8. And that is that number. If you divide 0.345 by 0.8, you get 0.431. So these are important results. Minimum so minimum length necessary minimum length necessary to develop bar force A sub B F sub Y is 345 F A sub B F sub Y divided by square root of F sub C prime. That is what we call development length, the length of bar needed to develop full F sub Y. For bars at relatively close spacing, the L sub D development length increases to 431 A sub B F sub Y over square root of F sub C prime. Okay. So with those basics in mind, we now go into ACI 318 and BNBC 2020. There are a lot of details, as I said in the beginning. Let us wade in and see what we can learn. Okay? So calculated tension or compression in reinforcement at each section of structural concrete members shall be developed on each side of that section. This is important. So calculated tension or compression in reinforcement at each section of structural concrete members shall be developed on each side of that section by embedment length, hook, headed deform bar or mechanical device, or a combination thereof. One way or the other, you have to develop the full stress. Now, if it is a continuum, if it is a beam, you are in the middle of the beam, there is plenty of reinforcement on two sides, development is automatic. Okay, you have the so-called embedment length. But if you are near the end, then you have to actively do something to make sure that the bar is developed. Anyway, this is very basic elementary stuff. I don't know that I need to spend a lot of time. So calculated tension or compression in reinforcement at each section shall be developed on each side of that section, and you do the development by embedment length, hook, headed deform bar, which I mentioned on the first day with you, or mechanical device, or a combination of these. Hooks and heads shall not be used to develop bars in compression. They work in tension fine, they do not work in compression. Hooks or heads. Okay, then as in the case of shear, square root of f sub c prime is restricted to no more than 8.3 MPa because we do not have experience enough test results with higher strength concrete. As the concrete strength increases, the development length, required development length decreases, but beyond a certain point, we are not sure that we should keep on decreasing the required development length because we do not have test results. Okay? So we do not, we restrict the strength of reinforcement to 10,000 psi. That again does not mean that you cannot use higher strength reinforcement, but it means that in your calculations you shall use F sub y equal to 10,000 psi. In the case of shear, there was an exemption. If you use higher shear reinforcement, then the limit doesn't apply. In the case of bond and development length, there is no such exception. So this is an absolute limit. Okay? In bond or development length calculations, I should say, square root of f sub c prime is limited to 8.3 megapascals. In addition to requirements in this chapter that affect detailing of reinforcement, structural integrity requirements shall be satisfied. I hope to go into the structural integrity requirements in the last concrete lecture, whenever that will be, module 8. That's what I have tentatively decided. Okay, so section 713 has structural integrity reinforcement that has to be provided no matter what, in addition to the requirements of this chapter. The strength reduction factor phi, this is very important. Moment, shear, torsion, we use a phi factor. Okay? The strength reduction factor phi is not used in the development length and lap splice equations. An allowance for strength reduction is already included in the expression for determining development and splice lengths. Okay? So I don't know that I can elaborate on that. So there is no phi factor in the expression for L sub D. what we are saying is something like a fee is already built in. So development length for deformed bars and deformed wire in tension. So now, from now on, I probably should indicate this. So first we will look at the code provisions for development length of deformed bars in tension, then development of deformed bars in compression, then development of hooked bars in tension. Hooked bars don't work in compression, so that doesn't arise. And then we will go on to other topics. So development length of deformed bars, also deformed wire in tension, shall be determined from either section this or section that, and applicable modification factors, etc. Importantly, L sub D shall not be less than 300 millimeters. Okay, this is an absolute minimum on development length of deformed bars in tension. Okay. The plain versus deformed I didn't bring up in our basic discussion. Plain bars is where we started. Plain bars have very little bond with concrete because the only bond is by adhesion and basically friction between, there is some rust or whatever on the reinforcing bar, friction between the bar and the concrete. And that bond is low, very easily overcome. That is why already in the 50s and 60s, we switched to these deformed bars, which greatly improves the ribs on the bars, greatly improve the bond between the reinforcement and the concrete. Today, basically all reinforcing bars are deformed. Yeah. So development length of deformed bars in tension, we have two different ways of figuring it, but the absolute minimum development length is 300 millimeters, 12 inches. Okay. There are two ways of doing it. First is using this table, and the second is there is an expression. Okay. This table has two columns. The first one is clear spacing of bars or wires less than d sub b, clear cover not less than d sub b, stirrups or ties. Okay, let me not. So read this. If this situation or that situation is satisfied, you use the first half of the table. All other cases, you use the second part of the table. Okay. So the second part gives you longer required development length. The 2.1 changes to 1.4, 1.7 changes to 1.1. In every case, well, first of all, this column is for number 19 and smaller bars and deformed wire. This is number 22 and larger bars. Okay, all deformed wires, irrespective of size, is in the first column. So every case, the required development length is so many bar diameters. Okay? 50 bar diameters, 62 bar diameters, whatever this number comes out to be. Okay? This has F sub y in it, the lightweight concrete factor lambda, the concrete strength, and also two factors we call psi sub t, the top bar factor, and psi sub e, the epoxy coating factor. Okay? So development length is so much, so many bar diameters. How many is a function of the yield strength of the reinforcement, the compression strength of the concrete, the lightweight concrete factor if there is lightweight concrete involved, and then two parameters, gamma psi sub t for top bar effect and psi sub e for epoxy coating effect. The top bar, I'll explain in just a little bit. So you have the choice of using the table, or you have the choice of using this expression. This is supposed to be a little more refined, little more exact. Here also, we have the yield strength of the reinforcement and the compressive strength of the concrete, the lightweight concrete factor gamma. Here we have an additional factor psi sub s, or bar size. So that is bar size factor, and we will look at what all those factors are. And then there is a term that deals with transverse reinforcement, confining reinforcement. Okay, the development length may be confined by transverse reinforcement, and that's what this term is about. Confinement term C sub B plus K sub TR divided by D sub B, this whole thing shall not be taken any greater than 2.5. So when you calculate it, if it comes out to larger than 2.5, you will take it equal to 2.5. The current expression, this is commentary for K sub TR, does not include yield strength of transverse reinforcement. And I'll let you read the rest of it because of time constraints. I think that is understandable upon reading why the yield strength of transverse reinforcement is not included. The K sub TR, but remember C sub B plus K sub TR divided by D sub B. One second. I think I may have forgotten the C sub B. Okay. K sub TR is 40, is a constant, times A sub TR divided by S and N. Okay, A sub TR, all the details will not register, so I will not try to over explain everything, but anyway, to just try to get a flavor of what this is. Okay, so A sub TR is total cross-sectional area of all transverse reinforcement within spacing S. All cross-sectional area of all transverse reinforcement within spacing S that crosses the potential plane of splitting through the reinforcement being developed. Okay, so you remember, it's some way to go back, but it may be worth it. So potential plane of splitting. So transverse reinforcement that goes through all the legs of transverse reinforcement, total area within spacing S that cross that plane of splitting. That's what we are saying here. Okay, so total cross-section area of all transverse reinforcement within spacing S that crosses the potential plane of splitting through the reinforcement being developed. N is the number of bars or wires being spliced or developed along the plane of splitting. This is very important. Not all the bars that there are, but the ones that are being developed or spliced. That is extremely important. K sub TR can be taken as 0 as a design simplification. that simplification we use surprisingly often, I would say. C sub B, which I forgot, it turns out, I will tell you, and I want to tell you the exact thing. C sub B is smaller of two things. The distance from center of a bar or wire to nearest concrete surface, and one half the center to center spacing of bars or wires being developed. Okay? So the distance from center of a bar or wire to nearest concrete surface, and one half the center to center spacing of bars or wires being developed, the smaller of the two. We will post a uh, revised slide set where C sub B will be indicated. Anyway, so C sub B is explained. Uh, I'm trying to get into the various things in this expression. Okay, C sub B, K sub T R, D sub B is just the bar diameter. So the factors psi sub T, psi sub S, and psi sub E. Okay, so psi sub T first, the top bar factor. What is a top bar? A top bar is a bar having more than 12 inches of concrete cast in one lift underneath the bar. So top bar is a reinforcing bar with more than 12 inches of concrete cast in one lift underneath the bar. If you have a top bar, size sub T is 1.3. The required development length goes up because of bleeding water that goes to the surface. The reinforcement is bonding with inferior concrete. That's what it boils down to. If it is other than top bar, we never use the word bottom bar. So it's top bar and other than top bar, then size of T is equal to 1. Epoxy coating factor used to modify. Okay, so size of E is 1.5 for epoxy coated bars with cover less than 3 diameters and clear spacing less than 6 diameters. Okay. So thin cover and close spacing, 1.5. 1.2 for all other epoxy coated bars or wires, and then 1.0 for uncoated and zinc coated reinforcement. So you get really penalized for epoxy coated bars that have thin cover on them and are closely spaced. 1.5 is the factor. The product of the two, the top bar factor and the epoxy coating factor, is has a ceiling of 1.7. You don't need to take it more than 1.7. And it is explained why we put this upper bound of 1.7 on the product of the two. The size effect factor, size of S, which is in the individual expression, not in the table. Size of S is 0.8 for, if I press in any way with this arrow, I go to the next slide, and that is, I have to keep myself from pressing. All I can do is to bring the arrow over, but I cannot push. Anyhow, so size of S is 0.8 for number 19 and smaller bars and deformed wire. Size of S is 1 for number 22 and larger bars. Okay, so this is bar size factor. Modification factor reflecting the lightweight concrete factor lambda is 0.75 for lightweight concrete, unless F sub CT specify the split tensile strength, then you can calculate it and it can be different from 0.75. Normal weight concrete 1.0. So lightweight concrete typically 0.75 is the lambda factor. And then there is another factor that I don't want to say complicated, but it causes some confusion. So reduction in L sub D, the required development length, shall be permitted where reinforcement in a flexural member is in excess of that required by analysis. So you have provided more reinforcement than required by analysis. So then you can take a reduction equal to the A sub S required divided by A sub S provided. Okay? So if you have provided more reinforcement than required by analysis, you can reduce the required development length by the factor between the required reinforcement and the provided reinforcement. Now, that seems simple enough. I said it leads to confusion because there are cases where you cannot take this reduction. And those cases are basically where the code ACI 318 specifically requires F sub y, full F sub y to be developed. That happens in high seismic applications all the time. That there are other cases where bars are specifically required to develop full F sub y. In those cases, you cannot take this reduction, okay? The excess reinforcement reduction. So that is explained here, and I will let you read. This tells you what I said, that when full F sub y is required to be developed by the code, you cannot take the excess reinforcement reduction. Okay. Now we come to development of deformed bars and deformed wire in compression. We go from tension to compression. Okay. So development length of deformed bars and deformed wire in compression, this is now L sub D C. L sub D is development length in tension. This is all required development length. L sub DC, required development length in compression, shall be determined from section 1232 and applicable modification factors. But L sub DC shall not be any less than, now it is 8 inches. Okay, so tension development length, barest minimum is 12 inches. Compression development length, it is 8 inches. Okay. These are the expressions for deformed bars and deformed wire. L sub DC, the required development length, is the larger of the values given by the two expressions. And the only parameters involved are F sub y, the yield strength of the reinforcement, the compressive strength of the concrete, F sub c prime, and the bar diameter. So nothing to explain. The factors that we can apply are factors that apply to the required L sub DC that you saw on the previous page. Factor used to modify development length based on reinforcement in excess of that required by analysis. So the same excess reinforcement factor, and modification factor of 0.75 where reinforcement is enclosed within spiral reinforcement, not less than 6 millimeter diameter, not more than 100 millimeter pitch. Okay, so let me read it again. You get a modification factor of 0.75. You get to reduce the required development length in compression by 25%, where your compression reinforcement is enclosed within spiral reinforcement, not less than 6 millimeter in diameter and not more than 100 millimeter pitch, or where your compression reinforcement is within number 13 ties in conformance with ACI section such and such, and spaced at not more than 100 millimeters on center. So number 13 or larger diameter bars, ties rather, at no more than 100 millimeters on center. So if you have confinement of one kind or another, you have a modification factor of 0.75, your required compression development length goes down. Okay. So required development length in tension, required development length in compression. Now development of standard hooks in tension. Okay, standard hooks are defined in ACI 318. And we may go into that a little bit on one or two of the slides. Standard hooks as defined in ACI 318. So development length for a deformed bar, no, development length for deformed bars in tension terminating in a standard hook. So we call this L sub D H. So, excuse me. L sub D is the required development length of deformed bar in tension. L sub DC required development length of deformed bar in compression. L sub DH required development of hooked bar in tension. And there will be after this L sub DT, that is something relatively new. That is the required development length of headed bar in tension. Okay, hooked bar and then headed bar. So hooked bar in tension L sub DH shall be determined from section such and such, and applicable modification factors. L sub DH has a minimum of 6 inches on it. Okay, so L sub D minimum is 12 inches. L sub DC minimum is 8 inches. L sub DH minimum is 6 inches. Hooked bar development length. Okay, this is the important expression for hooked bar development length. F sub y, F sub c prime, D sub b are the parameters. In addition, there is an epoxy coating factor, 1.2 for epoxy coated reinforcement. We don't increase it to 1.5 here for closely spaced and thin cover. Gamma is 0.75 for lightweight concrete. So those are the only two factors, size sub E and gamma. Size sub E and gamma shall be taken as 1.0 for other cases, meaning if you don't have epoxy coating, size sub E is 1, and if you don't have lightweight concrete, lambda is 1. So that is the expression. Now there are reduction factors that are allowed. This part gets a little bit complicated, and please follow me very, very closely. There are some pictures on after a few slides that will that I may go to and come back. So there can be a reduction factor of 0.7 on hooked bar development length. If you have number 36 bar and smaller hooks, so the hooked bars on number 36 are smaller in diameter with side cover, which is normal to plane of hook. Side, I think all of us understand, not less than 65 millimeters, 2.5 inches. And for 90-degree hooks with cover on bar extension beyond hook, not less than 50 millimeters. So the front cover, if you like, I don't know if upon reading this makes sense. So the hooked bar has to be no more than 36, number 36 millimeters in diameter. That's the first thing. So for 36 bar and smaller hooks with side cover not less than 65 millimeters, and for 90-degree hooks only with cover on bar extension beyond hook not more than 50 millimeters. I have a picture in a different context, but that may help. Let me go there. This going and coming back is time consuming and a little painful, but it's still worth it. Okay. So if you have a, let us say 90-degree hook and the bar diameter is no more than 36 millimeters and the side cover, which should be this cover, here, no more than 2.5 inches, and this cover from the end of the hook to the concrete surface no more than 2 inches. If that is the case, then you get a reduction factor of 0.7. Okay, then so that's one scenario. You may have a reduction factor of 0.8 for 90-degree hooks of number 36 and smaller bars that are either enclosed within ties or stirrups perpendicular to the bar being developed, spaced not greater than 3 diameter along L sub DH, or enclosed. This reading is too much. So what we are saying is 90-degree hook that has confinement reinforcement like this perpendicular to the bar being developed, and the spacing no more than 3 bar diameters, or you have confinement reinforcement like this, okay, parallel to the bar being developed, perpendicular to the hook, and the spacing here is also no more than 3 bar diameters. If you have one or the other, so for 90-degree hooks, number 36 and smaller bars, etc., those two pictures are described here. You get a reduction factor of 0.8. Also a reduction factor of 0.8 for 180-degree hooks of number 36 and smaller bars that are enclosed within ties or stirrups perpendicular to the bars being developed, spaced not greater than 3 bar diameters. That is understandable upon reading. And then even on the hooked bars, you can take a reduction factor, which is the required area of reinforcement divided by the provided area of reinforcement, where anchorage or development for F sub y is not specifically. So this again, like I said, for the when I talked about this reduction on the required development for intention L sub D, I said that when F sub y is specifically required to be developed, you do not get this reduction. Same thing with the hooked bars intention. If the bars are specifically required by 318 to develop full F sub y, then there is no reduction for excess reinforcement. Okay. So in the pictures that I showed you, the uh, confinement reinforcement perpendicular to the bar being developed or parallel to the bar being developed, the first tie or stirrups shall enclose the bend, shall be, so this is talking about the very first one being no more than 2 bar diameter from the end of the hook. Or in the other picture, this has to be no more than 2 bar diameter. The first one has to be placed within 2 bar diameters of the end of the bar or the hook. So that's all this is talking about. Standard hooks. Standard hooks are hooks that are shown in the picture. 90-degree at the top, 180-degree at the bottom. I do not know that I can add anything to what the picture shows. So I will let you look at it. These are the standard hooks of ACI 318. This you have seen for bars being developed by a standard hook at discontinuous ends of members with both side cover and top cover over hook less than 65 millimeters. The hooked bar shall be enclosed within ties or stirrups perpendicular to the bar being developed spaced. So this language describes this picture. Okay, so some situations you need this kind of transverse reinforcement. So after looking at the picture, maybe the language will make more sense. So for bars being developed by a standard hook at discontinuous end of members with both side cover and top cover over hook less than 65 millimeters, the hooked bar shall be enclosed within ties or stirrups perpendicular to the bar being developed, spaced not greater than 3 bar diameter along the hooked bar development length. The first tie or stirrup shall enclose the bent portion. Anyway, so it describes in detail. So if you have at the end of the beam, if you are developing the hooked bar, then you need this kind of transverse reinforcement. The picture is totally descriptive, and the language that I was reading describes the picture, and there is commentary on it that I'll let you read. As I told you, there are too many detailed requirements, which makes it very difficult to present this material. Okay, continuing with standard hooks in tension. Hooks shall not be considered effective in developing bars in compression. This has been said before. This is being said again. Hooks do wonders in tension, but do not work in compression. Okay, then development of headed and mechanically anchored deformed bars in tension. Now we are talking about L sub dt. Okay? So development length of headed deformed bars in tension shall be determined from section such and such. Use of heads to develop deformed bars in tension shall be limited to conditions satisfying A through F. So you cannot use headed bars in all situations. You have to satisfy conditions A through F. A, bar yield strength shall not exceed 420 MPa. Bar size shall not exceed number 36. Concrete shall be normal weight. Net bearing area of head shall not be less than 4 times the bar area. This is very important. Net bearing area of head shall not be less than 4 times the bar area. Clear cover for bar shall not be less than 2 bar diameters, and clear spacing between bars shall not be less than 4 bar diameters. Clear spacing not less than. Okay, that has been relaxed in subsequent editions, but we are on ACI 31808, so I don't want to take you into the future. Okay, so all those conditions, if all those conditions are satisfied, you can use headed bars for development or anchorage. For headed deformed bars, satisfying 359. 359 tells you about the ASTM. I have it on the next slide. Too many, too many annoyances. This thing pops up every, okay. Anyway, so headed bar satisfying 359. What does 359 say? Headed deformed bar shall conform to ASTM A970, and obstructions or interruptions of the bar deformations, if any, shall not extend more than 2 bar diameters from the bearing face of the head. So this is a headed bar. This is the bearing face of the head. Okay, this bears on the concrete. So the idea of headed bars is part of the stress is transferred from steel to concrete through bearing of the head on the concrete, and the rest of the stress is transferred by development along the bar. The disturbance, so this is the regular pattern of deformation of the bar that is disturbed at the end, but the disturbance, the obstructions must be within 2 bar diameters. Okay, so So these things that are different from the regular deformation shall not extend more than 2 bar diameters into the bar. That's what this is saying. So for headed deformed bars satisfying 359, development length in tension is as shown by the expression, again, f sub y, f sub c prime, psi sub e, and bar diameter, where the value of f sub c prime used to calculate L sub dt shall not exceed 40 MPa. This we haven't come across before, but with headed bars, we are imposing this limit. The value of f sub c prime used to calculate L sub dt shall not exceed 40 MPa, and the factor psi sub e, the epoxy-coated factor, shall be taken as 1.2 for epoxy-coated reinforcement and 1.0 for other cases. Okay, so the expression is not complicated, not very unlike the other expressions, but there are conditions for using headed bars, and then this additional restriction, the in calculating L sub dt, f sub c prime shall not exceed 40 MPa. Obviously, the concrete strength goes up, the required development length goes down. So this is L sub dt from the bearing face of the head to where the bar is fully developed. L sub dt headed bar development length, and then where reinforcement provided is in excess of that required by analysis, except where development of f sub y is specifically required as before. A factor as required over as provided may be applied to the expression for L sub dt. Length L sub dt shall not be less than the larger of 8 bar diameters and 6 inches. 8 bar diameters and 6 inches. Okay. This excess reinforcement factor has been eliminated from subsequent editions of 318. I don't remember when it went, but it went because here part of the stress transfer is by bond, only part. The remainder of the stress is transferred by bearing of the head on the concrete. Obviously, the stress that is transferred by bearing of the head on the concrete, that has nothing to do with this kind of reduction. It is only the stress that is transferred by development might be a logical candidate for a reduction. So this reduction factor has been dropped subsequently. But again, you are on 31808. I don't want to confuse you. This is what you will go by. Commentary on the reduction factor that I'll skip. Okay, continuing with development of headed and mechanically anchored deformed bars in tension, extending the bar to the far side of the column core helps to, so let me, there are two slides, no, one slide of writing. So what this is saying is this is something very sensible. So let us say you are developing that bar. Okay. L sub dt. So there has to be full development beyond the face of the column. If you are using head, L sub dt will take you up to here. So you can terminate the headed bar here. But ACI 318 is saying take it as far as you can, subject to adequate cover being provided and subject to no interference with the column bars. So although the head could be terminated here, take it as far as you can towards the face of the column, still keeping sufficient cover and not interfering with column reinforcement. This is being recommended because that way you grab more compression concrete. Are you with me? So if this bar tries to pull, it will have to take more compression concrete with it than if the bar terminated here, and that is desirable. You are not paying anything appreciable. So take the bar as far back as you can, although theoretically the bar needs to come only up to here. So this is specifically said in SEI 318. Heads shall not be considered effective in developing bars in compression, just like the hooks. Okay, any mechanical attachment or device, not just heads, capable of developing F sub Y of reinforcement is allowed, provided that test results showing the adequacy of such attachment or device are approved by the building official. Development of reinforcement shall be permitted to consist of a combination of mechanical anchorage plus additional embedment length of reinforcement between the critical section and the mechanical attachment or device. So all we are saying here is that it doesn't have to be a head. It can be some other mechanical device as long as there are test results to show that it works. Okay. Now it's a different topic, development of flexural reinforcement. If we are going to take a 5-minute break, I think this is a logical point. So let us take exactly 5 minutes. It is 17 after by my watch. So we'll come back at 22 after and continue. Okay.
Dr. Ghosh?
Yeah.
Do you want to disable the transition of slides on click? The mouse click.
Oh, I see. Yeah, that would be good.
Can you press escape from your keyboard?
Okay.
Yeah, go to transitions from the main, from the top. Yeah. And advanced slide, do you see at the right? Advanced slide. Ribbon menu, on the ribbon menu to the right. Just below share, the right.
So, say that one more time.
So, do you see advanced slide to the right? To the right of your screen.
Right of my screen.
Top right of your screen.
Slide. I do not see.
The close button. Do you see the close button of the presentation? Below the close button, there is a share button. Do you see that?
I don't.
Not here, not here. Yeah, this is review. Go right, go right, right,
Okay.
more right, more right.
Okay.
Here it is, advanced slide. Do you see that?
Oh, yeah. Okay.
Yeah, just uncheck on mouse click.
Oh, I see. Okay.
Now you can go to the.
And how do I get rid of this thing popping up all the time?
I cannot see it because you might not have shared the screen, right? So
Oh,
that
okay.
is not being shown to
Okay.
us, basically.
That's good. Okay.
That is just
Okay.
to you. Yeah.
Okay, good. That would be helpful. Yeah, because
Yeah.
that is really bothering me. Okay, thank you. 22 after. Okay, thanks.
Yeah. Now if you click, it won't. It shouldn't go.
Good.
Yeah.
Okay, it's time. I'll start again. I am pretty convinced now we have a time problem, so I do not exactly know. What I am thinking is, if necessary, I'll go all the way through to 11, and then the questions. I think Monday of next week, when I do two-way slab design for flexure, I think I can save some time and maybe take questions on this segment at that time. That would be one solution that I can think of. Today I kind of knew we had a problem. So anyway, so let us proceed. So
Dr. Ghosh, what
yeah.
we can do is that
Hmm,
Dr. Akib is also there. So what we can do is that me and Dr. Akib can answer the questions whatever that we can
hmm.
in your like when you're presenting, and like rest of the questions whatever that are left, then that we can address later.
Yeah. Okay.
Yeah.
Okay. So you are answering as I'm talking. That's what you're saying.
Yeah. So even Dr. Akib can see the question answer panel and can
I see.
also just click on Dr. Akib, just click on the question and you can then type in the answer and then send it. So you can type the answer.
Okay, sure. Okay, I can do that.
Okay.
So Dr. Ghosh, you can continue. Yeah.
Yeah, okay.
Yeah.
So development of flexural reinforcement, as you see, development of tension reinforcement by bending across the web to be anchored or made continuous with reinforcement in the opposite face of member shall be permitted. I don't know if it. So development of tension reinforcement by bending across the web to be anchored or made continuous with reinforcement on the opposite face shall be permitted. These are the bent bars that we used to use a long time ago. This is, at least in the US, there is absolutely no usage. I do not quite know about Bangladesh. Dr. Rakib would know. But this is not something I would like to spend time on. Okay, critical section for development of reinforcement in flexural members. This is not unimportant. So critical section for development of reinforcement in flexural members are at points of maximum stress, as you would imagine, and at points within the span where adjacent reinforcement terminates or is bent, where you cut off a bar or bent a bar up, that gives you a critical section right at that location. Okay? So points within the span where adjacent reinforcement terminates or is bent. Now this is vitally important. Okay, these are details that you absolutely must have very straight. So reinforcement shall extend beyond the point at which it is no longer required to resist flexion. Reinforcement shall extend beyond the point at which it is no longer required to resist flexure. It shall extend for a distance equal to d, the effective depth of the member, or 12 times the bar diameter, whichever is greater, except at supports of simple spans and at free ends of cantilevers. At those locations, there is no extension. Okay, but everywhere else, when you cut off a bar, it has to extend beyond where is no longer required by a distance of d or 12 diameters, whichever is the larger of the two. Continuing reinforcement shall have an embedment length not less than L sub d. So there are bars that are cut off, and then there are bars that are continuing. Continuing reinforcement shall have an embedment length not less than the tension development length beyond the point where bent or terminated tension reinforcement is no longer required to resist flexion. This, I think, will require a picture or so to become clearer, and I have plenty to show you. Now, very importantly, flexural reinforcement shall not be terminated in a tension zone. Okay, so where the bars are subject to tension. So flexural reinforcement shall not be terminated in a tension zone unless one of three conditions is satisfied. This is one out of three conditions, not all three, I want to emphasize. So flexural reinforcement shall not be terminated in a tension zone unless one of the conditions given are satisfied. First condition, V sub U required shear strength at the cutoff point does not exceed 2/3 of the design shear strength that we have at that section. So V sub U at the cutoff point required shear strength shall not exceed 2/3 of the design shear strength. That's condition number one. Condition number two, much more complicated. Stirrup area in excess of that required for shear and torsion is provided, this is in excess of that required for shear and torsion, is provided along each terminated bar or wire over a distance 3/4 of d from the termination point. Excess stirrup area shall not be any less than whatever, and then spacing shall not exceed 8/d times beta sub b, and that beta sub b is ratio of area of reinforcement cutoff, etc. I have not seen people use this condition to tell you the truth. Most of the time we go with this. Okay, one out of three conditions we typically go with this. This is much more complicated. The third one also is more complicated than the first one. For number 36 bars and smaller, continuing reinforcement provides double the area required for flexure at the cutoff point, and V sub U does not exceed, now it is 3/4 rather than 2/3, P times V sub N. So the first one was V sub U shall not exceed 2/3 P times V sub N. Pretty simple, straightforward. Now we are requiring V sub U not to exceed 3/4 of P times V sub N. And in addition, we are placing a limitation on bar size and are saying continuing reinforcement provides double the area required for flexion at the cutoff point. So why would one? So the first of the three conditions is the simplest, and we typically go with that. It is the summary of what I'm trying to tell you. Okay. This picture in out of ACI 318 commentary is a good one, and let me try not to point everything out, but let me talk about a few things. So at the support section there are those bars, the bars B and the additional bars. Okay, they don't have to be in two different layers. This is just showing, telling you that we have these two, what do I want to say? Some bars that are terminated, some bars that are not terminated. Okay, all the bars are at the support section. The bars that are not terminated are bars B, and the bars that are terminated do not have a name. The bars cannot be terminated short of one development length away from the support face, because at the support face, those bars have to be fully developed. Okay? So that's the first thing. Theoretical point of cutoff is here. We could cut the bars off here because here bars B can carry all the bending moments that need to be carried. But those bars, the bars that can be cut off, have to continue beyond the theoretical point of cutoff by D or 12 times d sub b, whichever is the larger of the two. Okay. And then the bars B have to have full development length beyond the theoretical point of cutoff here. Okay, so here the other bars are theoretically not required, but the bars that are continuing have to be fully developed. Okay. At the bottom, the C bars can be theoretically discontinued at this section X, and that's what the bending moment diagram shows. But they have to continue beyond by D or 12 bar diameters, whichever is the larger of the two. And these bars that are being cut off have to be fully developed beyond where they need to develop F sub Y, full development length, which is apparently this section. And then additionally, this has not come up in discussion so far. These bars that are continuing into the support must have L sub D for compression, or they have to satisfy 12.21 and 12.11 too. You can look those up. Anyway, so the illustration shows mostly what was said. What was said here. Okay, so the both of the things are important. The D or 12 bar diameter, but this is no less important, that the continuing bars have to have full development length beyond the theoretical point of cutoff. Okay. Adequate anchorage shall be provided for tension reinforcement in flexural members, where reinforcement stress is not directly proportional to moment, such as sloped, etc. This is a problematic area that is very difficult to provide definite guidance on. Okay? So let us take this bracket, corbel, whatever it is. Okay? So this reinforcing bar, first of all, at this phase has to be fully developed, and that would require L sub DH. Okay? This is a hooked bar. And if we provide L sub DH from the face of the column up to the end of the hook, the bar is fully developed. So that is not a problem. So the stress in the bar is F sub Y at this location. Normally, the bending is going down as you go to the right. So the stress in the bar should be going down, but not here, because bending is going down. The depth is also going down. So this bar very likely has close to F sub Y the entire way until the end. So how do you anchor it? How do you develop it? And the suggestion, most people would weld a rebar typically of the same diameter as shown in the picture, and that welded bar will provide the anchorage. So this figure is also in the commentary to ACI 31808. There is some language to go with the figure, and I would recommend that you get hold of it and read it. Okay. Now, so far it was development of reinforcement in flexure in general. Now this is development of positive reinforcement, positive moment reinforcement. Okay? So at least 1/3 the positive moment reinforcement in simple members, and 1/4 the positive moment reinforcement in continuous members shall extend along the same face of member into the support. So the bottom reinforcement in a beam If it is a simply supported beam, 1/3 must continue into the support. If it is a continuous beam, at least a quarter must continue into the support. In beams, such reinforcement shall extend into the support at least 150 millimeters. So if it is gravity design, I have a picture somewhere, I think. No. Anyway, so anytime I read or see, yeah, so at least a third of the positive moment in simple members, at least a quarter positive reinforcement in continuous members shall extend along the same face of member into the support. Fine. Extend into the support only means such reinforcement shall extend into the support at least 6 inches. So it's not continuous reinforcement. And whenever I see this, I flinch. Under gravity, it may be okay, but anyway, so this is where structural integrity reinforcement comes in, which I will discuss with you anyway in a week or in a week or 10 days maybe. I don't know. So but this is the requirement as far as the positive moment reinforcement goes. You extend it 6 inches into the support, and that is 1/4 of the positive reinforcement in continuous spans and 1/3 in simple spans. When a flexural member is part of a primary seismic force resisting system, positive moment reinforcement required to be extended into the support shall be anchored to develop F sub y in tension at the face of the support. This is a whole lot better. So this should require continuity. Okay? So when a flexural member is part of a primary seismic force resisting system, positive moment reinforcement to be extended into the support shall be anchored to develop F sub y in tension at the face of the support. So 6-inch extension now is not going to do. This is extremely, extremely important for you to note. At simple supports, still continuing positive reinforcement, at simple supports and at points of inflection, positive moment reinforcement shall be limited to a diameter such that L sub D, this gets a little, this gets a little complicated. So what we are talking about here is at, so 2 locations, at simple supports and at points of inflection. We are trying to limit the bar diameter, the bar size. We do not want a small number of large bars. We want a larger number of smaller bars because that's better for bond. Okay? At simple supports and at points of inflection. Now we limit the bar size by instituting this restriction. L sub D development length shall not be any larger than M sub N. So we are talking about, remember, a simple support or a point of inflection. So everything is at that location, and I have pictures. So M sub N divided by V sub U, M sub N is the nominal flexural strength. And it says here, assuming all reinforcement at the section is stressed to F sub Y, all the reinforcement is yielding, divided by V sub U is simply the calculated required shear strength at the section, plus L sub A at support. So we are at a support or at an inflection point. If we are at a support, then L sub A shall be the embedment length beyond center of support or if we are at an inflection point, L sub A shall be limited to D effective depth or 12 bar diameters, whichever is greater. Okay, so L sub D, we will be limiting bar size by requiring L sub D to be no more than something. Okay, so the larger the bar diameter we want to use, the larger the required development length. So if you use too large a bar diameter, you'll be in violation of this requirement. If you have small bar diameter, L sub D will be small, and then you'll be in compliance with this requirement. That's the idea. Okay, it is being done somehow uh, uh, indirectly. Now, an increase of 30% in the value of M sub N over V sub U shall be permitted when the ends of reinforcement are confined by a compressive reaction. So at the support, if the support reaction provides compression, okay, the beam is pressing down, the support is pressing up, compression is created. Under that situation, you get to multiply M sub N over V sub U by 1.3. So L sub D now can be larger. The required development length can be larger, which means the bar size can be a bit larger if the support provides compression. So that's what we are saying. An increase of 30% in the value of M sub N over V sub U shall be permitted when the ends of reinforcement are confined by a compressive reaction. Okay. So this is in picture. So we are at a support. This is the embedment length, L sub A, and this is M sub N over V sub U. We have multiplied by 1.3, assuming that this support provides compression. So maximum development length would be from here to there. So your bar size has to be such that the required development length does not exceed this maximum development length. Here we are at an inflection point. Inflection point. The M sub N over V sub U distance is this. The D or 12 bar diameter distance is this. So maximum L sub D in this case is this distance from here. So the maximum development length is from here to there. M sub N over V sub U in one direction from the point of inflection, and 12 bar diameter or D sub B in the other direction from the point of inflection, the two added up to the maximum development length. So the bar diameter cannot exceed a certain value, which will take the required development length beyond the maximum development length. Okay. Now it is specifically deep beams. At simple supports of deep beams, positive moment tension reinforcement shall be anchored to develop F sub Y in tension at the face of the support, except that if design is carried out using etc. etc. This I'll let you read the rest of it. But the key thing is at simple supports of deep beams, positive moment tension reinforcement shall be anchored to develop full F sub Y in tension at the face of the support. Okay, there is an exception to that. Now, development of negative reinforcement. I don't think you ever suspected that this development is such a problem, but ACI has very systematic, and this is all because of problems that have been observed and testing. That's the basis. Okay, so development of negative moment reinforcement. Negative moment reinforcement in a continuous restraint or cantilever member or in any member of a rigid frame shall be anchored in or through the supporting member by embedment length, hooks, or mechanical anchorage. I don't want to elaborate on that. I think that's understandable. Negative moment reinforcement shall have an embedment length into the span as required by ACI section such and such. Now, this is important. At least 1/3 of the total tension reinforcement provided for negative moment at a support. At least 1/3 the total tension reinforcement provided for negative moment at a support shall have an embedment length beyond the point of inflection, not less than D 12 bar diameters or 1/16 of the span, whichever is greater. Okay, so at least 1/3 of the total tension reinforcement provided for negative moment at a support shall have an embedment length beyond the point of inflection. This is negative reinforcement, not less than D 12 bar diameters or L sub n over 16, whichever is greater or greatest. At interior, this is now deep flexural members. At interior supports of deep flexural members, negative moment tension reinforcement shall be continuous with that of the adjacent spans. That doesn't give you any choice. Just say it's continuous. So, development of negative moment reinforcement. This is a simple, straightforward picture. If you are terminating in this exterior column, all you need is hook bar development length, provided you have a standard hook at the end. However, this is the what we were talking about in beyond inflection point. Okay, so this is obviously a negative bar at the base of the support. We have to have the bar fully developed. That would require development length, straight bar development L sub D. So the bar needs to continue for at least L sub D this way. This is the point of inflection. Negative moment changes to positive moment. Okay, so the negative bar has to extend beyond this point of inflection by, remember, D 12 bar diameters or 1/16 of the span, whichever is the largest of the three. I think this is a very clear-cut picture of what it is that we have to do. Okay, so development of flexural reinforcement, development of positive reinforcement, development of negative reinforcement. Now, development of web reinforcement. Okay, this is the stirrups and things that you use. Now here, quite a bit of how should I say, quite a bit of the provisions is devoted to welded wire reinforcement being used as stirrups or shear reinforcement. I do not know how widespread that usage is in Bangladesh, welded wire reinforcement being used as stirrups. And so I thought last night or early morning, whenever I was looking at this stuff, at this portion of the presentation, that those are probably things that I will skip. And obviously you will have the slide set. You can read. You can go to BNBC or 318, but I probably will not spend time discussing that. So, development of web reinforcement. Web reinforcement shall be, this is important, as close to the compression and tension surfaces of the member as cover requirements and proximity of other reinforcement permits. This is actually a requirement. Okay, web reinforcement shall be as close to the compression and tension surfaces of the member as practical. Ends of single leg, simple U, or multiple U stirrups shall be anchored as required by section such and such, A through, no, 0.1 through 0.5. So the BNBC numbering is A through E. So ends of simple single leg, multiple U, or simple U stirrups shall be anchored as required by 12, 13, 2, 1, 2, 2, 2, 3, 2, 4, or 2, 5. 5 different ways of anchoring. Okay. Number 1, for number 16 bar and MD200 wire, I explained the wire size. M is metric, D is deformed, 200 is 200 square millimeter cross-sectional area. So for number 16 bar and MD200 wire and smaller, and for number 19, number 22, and number 25 bars with F sub YT of 280 MPa or less, this is the old 40 KSI steel, a standard hook around longitudinal reinforcement. That's all you need. Okay. So for the small bars and for the larger bars, if it is grade 40, then all you need is a standard hook around longitudinal reinforcement. So you have stirrups, you will have standard hooks around longitudinal reinforcement, and your stirrups are fully developed. For number 19, number 22, number 25 stirrups, F sub YT greater than 280 MPa. So now this is larger bars and kind of standard 60 KSI, whatever, not the old 40 KSI strength. A standard stirrup hook around a longitudinal bar, you have to have the hook, plus an embedment between mid height of the member and the outside end of the hook equal to or greater than the given quantity. So you have to have a minimum distance between the hook and the mid height of the member. Okay, so if you again, if you fall short, then you probably have to go with thinner bar for the stirrup. The D sub B has to decrease. If decreasing F sub YT does not make a lot of sense, and increasing concrete strength will probably also not make a lot of sense. But normally you wouldn't have that problem. So just try to get an idea. That's all we do now. So for the larger bars that are not grade 40, these are large size stirrups, number 19, 22, 25. These are, yeah, not terribly common, I would say. Standard stirrup hook around a longitudinal bar plus an embedment between mid height of the member and the outside of the hook equal to or greater than the quantity given. Okay. So that was 2, this is 3. For each leg of welded plain wire reinforcement, so I will skip this one. For one longitudinal wire located not more than D/4, this is also welded wire reinforcement used as shear reinforcement. Development of web reinforcement for each single leg stirrup web. So this is also welded wire fabric. Okay. In joist construction. Joist construction is defined in ACI 318. The ribs, you know what joists are. The ribs have to be 3 feet apart, and there are size restrictions. Anyway, joist construction has to meet the definition of joist construction in ACI 318. And if you have the if you have legitimate joist construction as defined in 318 section 8.11 for number 13 bar and MD 130 wire and smaller, all you need is a standard hook. So these are in joists, you typically have one leg of these vertical bars as shear reinforcement, and all you need are standard hooks. Between anchored ends, each bend in the continuous portion of a simple U-stirrup or multiple U-stirrup shall enclose a longitudinal bar. This is extremely important, okay? So between anchored ends, just imagine a simple U-stirrup. So there are two anchored ends. The two ends of the U hook around longitudinal bars. But then this U, okay, so you start with let us say the left bar to the top. The stirrup hooks around that, comes down, then it goes around a bottom bar, and then it goes again around another bottom bar, and then goes up, and then hooks around the top right bar. Now we are saying that when it makes these bends, I said around the bottom bar and then again around the bottom bar, there needs to be bars at those locations. So you should not bend a stirrup and not have the bend supported by a longitudinal bar. So between anchored ends, each bend in the continuous portion of a simple U-stirrup or multiple U-stirrup shall enclose a longitudinal bar. Okay. These are bent bars. This I also would like to skip just to save time. I think we have more important stuff to discuss. So this is development of web reinforcement, but we are talking about bent bars. Okay, this one I think I should discuss. So pairs of U-stirrups. So the idea here is you take two U's. One, the verticals are going up, and then in another, the verticals are going down. You put one on top of the other to make a closed hoop. That's the idea, or hoop-like thing. So pairs of U-stirrups or ties so placed as to form a closed unit. So pairs of U-stirrups or U-ties so placed as to form a closed unit shall be considered properly spliced when length of laps. So those U's will have to lap in the middle. And the lap length has to be 1.3 times the L sub D of the bars making up the U's. This is the first thing. Then we consider them to be properly lapped. Now in members, at least 450 millimeters in depth, such splices with A sub B, F sub YT not more than 40 kilonewtons per leg shall be considered adequate if stirrup legs extend the full available depth of a member. I think you can read that and understand. I don't know that I can add any explanation. Anyway, this is two U's making up a closed unit that is provided for. Now it's a totally different topic. Okay, so try to remember. So we started with development of deformed bars in tension, L sub D. Then development of deformed bars in compression, L sub DC. Then development of hooked bars in tension, L sub DH. Then development of headed bars in tension, L sub DT. Then we went to development of flexural reinforcement. We talked separately about top reinforcement and bottom reinforcement, or positive reinforcement and negative reinforcement. Okay. Then we got into the development of web reinforcement, which is typically there for shear. Okay. Now, for the first time, we are coming to the big topic of splices of reinforcement. Okay, yeah, just so that we know exactly where we are. Splices of reinforcement. Splices of reinforcement shall be made only as required or as permitted on design drawings or in specifications or as authorized by the licensed design professional. You cannot just do it. Okay. So splices of reinforcement shall be made only as required or permitted on design drawings or in specifications or as authorized by the licensed design professional. Lap splices shall not be used for bars larger than number 36 except as provided in section such and such. Okay, there are exceptions, but normally you cannot lap what we call number 14 and number 18. I think those are 43 millimeters and 56 millimeter bars. So lap splices shall not be used for bars larger than number 36. Number 36. Except as provided for. Those exceptions may come up. I don't remember. Okay, bars spliced by non-contact lap splices. There are such things. Lap splices, the bars that are being lapped do not necessarily have to be in contact. There are non-contact lap splices. And you can transfer stress by non-contact lap splices. Bars spliced by non-contact lap splices in flexural members shall not be spaced transversely further apart than the smaller of 1/5 the required lap splice length and 150 millimeters. So if it is a non-contact lap splice, the bars that are being lapped or spliced should not be too far apart from each other. Okay, the maximum distance is 6 inches or 1/5 the required lap length, whichever is smaller of them. Yeah, why no laps on the larger bars? Because of lack of adequate experimental data on lap splices on number 43 and number 57 bars in compression and tension, lap splicing of these bar size is prohibited except as permitted in those two sections for compression lap splices of number 43 and number 57 bars with small. So the only time the laps, any kind of lap splicing with number 43 or number 57 bars would be permitted is when those large bars are lapped with smaller bars. Okay. So that's basically what it is. Otherwise, they cannot be lapped. For one thing, the lap length will be something horrendous for those large bars. Mechanical and welded splices. Mechanical and welded splices shall be permitted, first of all. A full mechanical splice shall develop a tension or compression as required of at least 1.1 1/4 f sub y. This is important. So a so-called full mechanical splice develops 125% of the yield strength of the bar that it is splicing. Mechanical splices actually are very, very attractive in many situations because the laps can be long for larger bars. gives you congestion, and placement of concrete becomes difficult. However, mechanical splices are expensive, and they also take up room. Particularly in a congested situation, imagine a column typically will not have only peripheral reinforcement. There may be interior reinforcement. How would you get in there to install the mechanical splices? So there are limitations. How should I say? It is an attractive solution provided you can afford it, and provided you have access to the bars on which mechanical splices are to be installed. Okay? So anyway, full mechanical splice develops 125% of the yield strength of the bar. Except as provided in this code, all welding shall be by AWS D1.4. This is, I don't know, there must be parts of the world where that is not followed, but in a large part of the world, AWS, that's American Welding Society, D1.4 is what is used for welding. A full welded splice shall also develop 125% of the yield strength of the bar that it is splicing. Mechanical or welded splices not meeting requirements, the full 1.25 F sub y shall be permitted. So less than full mechanical or welded splices shall be permitted only for number 16 bars and smaller, and in accordance with a section that gives you a number of other conditions. So you cannot just do it willy-nilly. It has to be smaller bars, and there are conditions attached. They're pretty onerous conditions. This less than full mechanical splices, welded splices, has been deleted from ACI several editions ago. We don't have them anymore. You are looking at it because you are still on ACI 31808, and I don't want to, how should I say? So I need to tell you that it is in there. However, these things probably should be discouraged. If you are going for mechanical or welded splices, use full mechanical or welded splices. This less than full on the thinner bars, I think it makes limited sense and it complicates things. Okay, so okay. Lap splices. So minimum length of lap for tension lap splices shall be as required for class A and B splice. There are class A and class B lap splices, but not less than 300 millimeters, not less than. So lap splice length cannot be any less than 12 inches. Minimum length of lap for tension lap splices shall be as required for class A or B splice, but not less than 300 millimeters. Class A splice, the splice length is 1 time development length. Class B splice, it is 1.3 times development length in tension. L sub D is calculated to develop F sub Y, but without the 300 millimeter minimum of ACI. So the L sub D, that so splice length is either 1 or 1.3 times development length. Splice length has a minimum on it of 300 millimeters. So when we calculate development length by ACI 318 requirements, you remember there was a table and an expression. You could use the table or the expression. The development length itself had a minimum on it of 300 millimeters, 12 inches. So if it is a class B splice and the splice length is 1.3 times development length, the minimum will apply on the splice length, not on the development length. So we are saying that when you calculate the development length, forget about the 300 millimeter minimum on it. It's a calculated development length that we want. And the modification factor for excess reinforcement, if you have taken that, forget that. Okay, don't bring that over in calculation of splice length. So splice length is 1 or 1.3 times development length. The development length is calculated without a minimum of 300 millimeters on it, and it must be without any excess reinforcement factor. Okay, this is saying that there has been a lot of people have told 318 that two classes of splices don't make any sense, but we continue to maintain them for reasons that are given. Okay, lap splices of deformed bars and deformed wire in tension shall be class B. So all splices shall be class B unless you satisfy two conditions in which your splices can be class A. Okay? So if you can satisfy two conditions, your splices are class A. If you cannot satisfy those two conditions, your splices are class B. What are the two conditions that will qualify for class A splices? The area of reinforcement, provided is at least twice that required by analysis over the entire length of the splice. This is obviously very important. So the area of reinforcement provided is at least twice the area of reinforcement required by analysis over the entire length of the splice. This is number one. Number two, 1/2 or less of the total reinforcement is spliced within the required lap length. Okay, if you have 4 bars, you cannot splice more than 2 bars within the lap length. If you have 6 bars, you cannot splice more than 3. So you must have at least twice as much reinforcement as is required by analysis, and you cannot cut off more than half the bars within the lap length. If you satisfy both conditions, you have a class A splice. Otherwise, you have to use a class B splice, 1.3 times development length. When bars of different size are lap spliced in tension, this is important. When bars of different size are lap spliced in tension, splice length shall be the larger of development length of the larger bar and tension lap splice length of the smaller bar. Okay, I will read it one more time because this is extremely important, and please pay attention. When bars of different sizes are lap spliced in tension, splice length shall be the larger of development length of the larger bar and tension lap splice length of the smaller bar. Okay. Mechanical or welded splices used where area of reinforcement provided is less than twice that required by analysis shall meet requirements of 12, 14, 3, 2, etc. So mechanical and welded splices used where area of so what this is saying is that if you're going to use mechanical or welded splices where area of reinforcement provided is less than twice that required by analysis, then you have to go for full welded or full mechanical splice. Though those less than full splices will not do. Okay, that's what those two sections are: full mechanical splice, full welded splice. So If you are going to use mechanical or welded splice where area of reinforcement provided is less than twice that required by analysis, then you have to have full welded or full mechanical splices. Now, less than full mechanical or welded, that is 1255. Mechanical or welded splices not meeting the requirements of those two sections, full mechanical or welded, shall be permitted. First of all, for smaller bars, number 16 bars and smaller, if three requirements are met, 0.1, 0.2, 0.3. And I don't even want to spend time on those because I would really like to discourage this less than full mechanical splices. You can use them on smaller bars, provided you satisfy three requirements given in these three sections, and let us not spend time on those conditions. Okay. Splices of deformed bars and deformed wire in tension. We are on the same subject. Splices in tension tie members. These are tension tie tension members. Splices in tension tie members shall be made with a full mechanical or full welded splice in accordance with section such and such, and splices in adjacent bars shall be staggered at least 750 millimeters. So tension tie members in concrete are not commonplace, but if you have them, this is a member subject to tension. All the tension obviously has to be taken by the reinforcing bars. Concrete doesn't carry any. So if you have to splice them, it is full mechanical or full welded splice. And very importantly, the splices in adjacent bars shall be staggered at least 750 millimeters. Splices of deformed bars in compression. Compression lap splice length shall be, so 071 F sub y D sub B for F sub y of 420 MPa or less, or another expression for F sub y greater than 420 MPa, but not less than 300 millimeters compression lap splice length. For F sub C prime less than 21 MPa, length of lap shall be increased by 1/3. Okay, so compression lap splice length and expression is given. It's a function of, so it is so many bar diameters. These so many bar diameters is a function of the yield strength of the reinforcement, and the minimum compression lap length is 300 millimeters. And very importantly, for F sub C prime less than 21 MPa, length of lap shall be increased by 1/3. Splices of deformed bars in compression. Continuing, when bars of different size are lap spliced in compression, this is not uncommon at all. When bars of different size are lap spliced in compression, splice length shall be the larger of the compression development length of larger bar and compression lap splice length of smaller bar. This is very similar to what we had for tension. Lap splices of number 43 and number 57 bars to number 36 and smaller bars shall be permitted. See, this is where lap splices are permitted of the number 43 and number 47 to smaller bars. So lap splices of 43 or 57 bars to number 36 and smaller bars shall be permitted. Mechanical and welded splices used in compression shall meet requirements of section such and such. There are two different sections. Well, and the sections are full mechanical and full welded. So mechanical or welded splices used in compression shall be full mechanical splices or full welded splices. That less than full business does not apply. This is commentary. Lap splices are generally prohibited for number 43 and number 57 bars. However, for compression only, lap splices are permitted for number 43 and number 57 to number 36 or smaller bars. End bearing splices. There are such things in compression. So in bars required for compression only, transmission of compressive stress by bearing of square cut ends held in concentric contact by a suitable device shall be permitted. I don't know that I should spend time on this. Okay, so it is shortly before 10:30. I do want to cover the examples to the extent I can. And then, as I said, we'll leave the questions. I don't have any expectation that will be done substantially before 11. Let us see what happens. Okay, so this is the first example is bar cutoff in beams. So a beam, this is the end span. It continues over several spans, more than 2, it says. 115 kilonewton per meter is the uniform load. 6 meter clear span. We are using deliberately the same beam for different examples, so you can compare, put things together. 400 by 550 is the section dimension. Concrete strength 40 MPa, and the steel strength is 420 MPa. We are going to use the ACI moment and shear coefficients given in section 833. And by those coefficients, those look very crude, but they're not bad at all. Or anyway, I will not go into that, but you shouldn't have any qualms about using these simple looking ACI coefficients for design purposes, particularly gravity design. So according to these ACI coefficients, negative moment at interior face of exterior support for members built integrally with columns. So negative moment at interior face of exterior support. Bending moment here, okay, is W ln square over 16, and that comes in our case to 259 kilonewton meters. W sub U is the 1.15, 115 kilonewton per meter. L sub N is 6 meters given. So the W is there, L sub N is there. Okay, so 259 kilonewton meters. Negative moment at exterior face of first interior support, WL square by 10, that comes to 414 kilonewton meters. And positive moment in the end span, 1/14 of WL square, and that comes to 296 kilonewton meters. So 259 at one end, 414 at the other end. These are negative moments, and the positive moment in the span is 296. For the 296 positive reinforcement in the span, we provided 2 number 25 bars and 2 number 28 bars. And that gave us phi times m sub n of 376, which being in excess of 296, it's fine. Top reinforcement at the exterior support, we have a moment of 259 kilonewton meters. We used 4 number 25 that gave us design moment strength of 338, which is obviously in excess of 259. Top reinforcement at the interior support, where you have a large moment of 414. Here we have used 4 number 32 bars, and that gives us a phi times m sub n of 526 kilonewton meters. Okay, so that's our flexural design, if you like. At the exterior support section, 4 number 25 bars, where the required moment strength was 259. At the interior support, it is 4 number 32, where the required moment strength was 414. And in the span, it is 2 number 25 plus 2 number 28. Shear. By the same table, ACI coefficients, section 833, shear in end members at face of first interior support, that is the largest, 1.15 WL by 2, and at every other support it is 1.0 times WL over 2. So 1.15 WL by 2 comes to 397 kilonewtons of shear. With number 32 bars at the interior support, the effective depth is 550 total depth minus 40 millimeters of clear cover minus the diameter of the 12 millimeter tie or stirrup or whatever, minus half the diameter of the longitudinal bar. That comes to 482 millimeters. So at critical section for shear at a distance d from the support face, so at the support face we have a shear of 397. The effective depth is 482 millimeters. So the critical section is 482 millimeters from the support. At that critical section, the shear goes down from 397 to 342 kilonewtons. Okay. The shear that concrete can carry, 0.17 square root, in our units 2 square root of F sub C prime, comes to 208 kilonewtons. So we have a shear of 342 required shear strength. Concrete can carry 208. We said let us provide 2-legged number 12 stirrups at 160 millimeter spacing. That will give us a V sub S of 288 kilonewtons. So concrete can do 208. The 2-legged number 12 stirrups can do 288. Combined and reduced by the phi of 0.75 gives us 372 kilonewtons, which is greater than the 342 that we need to take at the critical section. So we have our flexural reinforcement, we have our shear reinforcement, 2-legged number 12 stirrups. Okay, so this is the picture. We have at the exterior support section 4 number 25 top bars, in the span 225 and 228, and at the interior support section 4 number 32. Okay, and then those are the bars that will be, so we have 2 number 25 and 2 number 28 at midspan. Some of those will have to continue into the supports. Remember, at least a third or at least a quarter. Anyway, for construction reasons, we need to continue 2 bars. So the decision has been made to continue the two number 25 bars, and at the top, these are also two number 25 that are continuous. So here, out of the photo number 25, two are cut off, the other two continue, and then they lap with the number 32 bars. That's what you are looking at. Okay. So here are the calculations. At least 1/4 of the positive reinforcement in continuous beams needs to be extended into the supports by 150 millimeters. This is the 3810 requirement. In this case, at least 2 bars need to be extended in order to hold the stirrups in place. As I said, for construction reasons, you have a stirrup, you need to hang it around bars. So we need at least 2 bars. Thus, 2 number 25 bars in the bottom reinforcement are extended into the supports, and the 2 number 28 are terminated away from midspan. Okay, makes sense. 2 number 25 are continued, 2 number 28 are cut off at suitable locations. So determine the cutoff location for the 2 number 28 bars. Loading condition for maximum positive moment. Okay. For maximum positive moment, apply the lower of the two support moments, in our case the 259 kilonewton meters at the appropriate support, and the midspan moment, so 259, 250, 296, where remember 259 at the exterior support, 296 in the span. This is at the very first page of the example. So when it comes to cutting off of the positive bars, we consider loading condition for maximum positive moment. Apply the lower of the two support moments at the appropriate support. In our case, 259 at the left support, and the midspan moment 296 kilonewton meter at midspan, to calculate the left reaction R sub L and the right hand moment M sub R. Okay, this moment we did not take from page 1 because this moment and the two moments on page 1 are not simultaneous. Okay, those are estimates of the largest moments that we should design for. They do not exist at the same time. So we have to calculate this from that. If the moment at the left support is that, what is the moment at the right support? That has to be calculated. So so the beam with the load on it, 259, etc., taking moment about midspan. So there is a moment of 259 counterclockwise. Midspan would be 3 meters from the left. This reaction will cause a moment R sub L times 3, which is clockwise. So this is negative. And then 115 kilonewton per meter over 3 meters of span will cause a moment of so much, which is also counterclockwise. So it is positive, and 296 being a positive moment is also counterclockwise, and it is positive. So this is so if we take moment about midspan, we get this equation from which the left reaction comes out to 357.5. And by taking moment about the right support, the right hand moment comes out to 184 kilonewton meters. Okay. 184 kilonewton meters, not the value that we designed the section for. So now we have our bending moment diagram, 259 at this support, 184 I think is the calculated value at that support, and 296 is the span moment. Okay, so from this diagram, we can see that we can calculate that the inflection point is 0.84 meters from the left support and 0.62 meter from the right support. After two number 28 bars are cut off, flexural strength provided by the two continuing number 2 bars it has to be calculated. So we calculate the stress block depth for the remaining two number 25 bars. That comes to 30 millimeters. Effective depth is 485.5 calculated value. Nominal moment strength comes out to 193 kilonewton meters. So design moment strength is 174 kilonewton meters. So 174 is here, 174 is, so this is the bending moment diagram. 259 at the left end, 184 at the right end, 296 in the middle. This is 174 where the 2 number 28 can be theoretically cut off, and this is also where 2 number 28 can be theoretically cut off. This is 1.4 meters from the right hand side and 1.6 meters from the left. So 2 number 28 bars need to extend by D or 12 bar diameters, whichever is greater, beyond points 1 and 2. So theoretically, it can be cut off here and there because we have enough moment strength coming from the remaining 2 number 25 bars. But we have to go beyond the theoretical point of cutoff by 12 bar diameters or the effective depth. The effective depth is calculated at 484 millimeters. 12 bar diameter is 336. So the 484 millimeter governs. Okay, 484 millimeter governs. So terminate 2 number 28 bars at, so what was the number? 484 millimeters is the required extension beyond where the bars can be theoretically cut off. Okay. So terminate 2 number 8 bars 1.1 meters. So this is 0.84 meters. Another another 0.48. So 84 plus 4. No, I somehow got I mixed up the pages. So 484 is the extension, right? So terminate 2 number 28 bars, 1.1 meter from left support face and 0.9 meters from the right support face. So so this is 1.6 meters. If you take away the 0.484, basically 0.5. Theoretically, the bars can be cut off here, but they need to go another half a meter. So that will give you termination point 1.1 meters from the left support. These bars can be terminated here at 1.4 meters away, theoretical point of cutoff, but you need to go another 0.5. That gives us 0.9 meters from the right support. So the number 28 bars are cut off 1.1 meter from the left support and 0.9 meters from the right support. Okay, I'm sorry, I was mixing up the pages. So that's all that happened. Now to continue, the continuing two number 25 bars need to have a minimum embedment L sub D beyond points 1 and 2. Remember, at points 1 and 2, the continuing bars have to be fully developed. Now, what is the development length of these bars? Here comes the expression of ACI 318, and without going into all the details, the calculated development length of the continuing number 25 bars comes to 585 millimeters. There is a minimum of 300 millimeters that doesn't govern. So 585 millimeters is L sub D. So two continuing number 25 bars extend much more than 585 millimeters beyond points 1 and 2. Okay? You have plenty of room. So needed is 585 millimeters. The continuing bars go significantly beyond 585 millimeters. So we are fine in that regard. Okay, check at least one requirement out of, so we are terminating the bars, the positive bars in a tension zone. Okay, the bars are still in tension. So at least one requirement of remember, there were one of three requirements had to be met if we wanted to terminate bars in a tension zone. So that's what we are checking now. So V sub U at cutoff point cannot exceed 2/3 phi times V sub N. V sub U at cutoff point was, so cutoff point, remember, is 1.1 meters from the left face. And in that location, the V sub U is calculated as 231 kilonewtons. This side, it is 229 kilonewtons. Phi times V sub N at cutoff point is 372 kilonewtons. You can go back to our design for shear and you will see that that number is there. I don't want to go back so many pages now. So 2/3 of P times V sub N is 248, and this V sub U of 231 being less than 2/3 of P times V sub N or 248, we are okay. So we can terminate the two number 28 bars in the tension zone as we have done. Then the check on bar size. Remember, bar size cannot be any larger than something. So this condition has to be checked. L sub D cannot exceed M sub N over V sub U plus the embedment length. At the point of inflection, only two number 25 bars are present. Okay? At the point of inflection was 1.4. Anyway, let us take, you can check back. I'm sure that this statement can be verified because it is getting late. So at the point of inflection, only two number 25 bars are present. L sub D was calculated as 585 meter. M sub N is 193 kilonewton meters. This is the 174 divided by 0.9. Okay, the 174 was the moment diagram before here. Okay, so this is the number. At the inflection point, there are only two number 25 bars. The number 28s have been discontinued. So yeah, so at point of inflection, only two number 25 are present. L sub D is 0.585. M sub N is 193 kilonewton meters. V sub U can be calculated at 261 kilonewtons on one side, 61.5 on the other side. So at the point of inflection, L sub A is the greater of D or 12 bar diameters. D in our case is 485.5, 12 bar diameters is 300, so this governs. So M sub N over V sub U plus LA is 193, M sub N, V sub U of 261.5 plus L sub A of 485, that is 1.22 meters. That being larger than that, the development length cannot exceed 1.22 meters. Our development length of 485 is way less than 1.22 meters. So we are fine. So that, okay. So far everything has checked out. Now loading condition, now the top reinforcement cutoff. Remember we have 4 number 32 at one support, 4 number 25 at the other support. So loading condition for maximum negative moment. We take the maximum negative moment from page 1. Okay, so assume a condition where the calculated M sub U is acting at each support and calculate the midspan moment based on that. So the so 414 and 259, the calculated moments are, assume a condition where the calculated M sub U is acting at each support and calculate the midspan moment. That's what we are doing here. 115 kilonewton per meter load is sitting on the beam. So taking moment about right support, the reaction comes to so much. So midspan moment, to cut a long story short, comes to 1803.5 kilonewton meters. Determine cutoff location for top reinforcement. Loading condition for maximum negative moment is 414 here, 259 here, 1804.5 here. So So this is the bending moment diagram that we are dealing with. Loading condition for maximum negative moment. Now, at least 1/3 of the total negative reinforcement at supports needs to be extended beyond the point of inflection by not less than D or 12 bar diameters, or L sub N over 16 top bars, remember compression bars. So D 12 bar diameters or L sub N over 16. So check requirement, so extend all 4 number 32 bars at right support up to 2 meters from the support face. Extend 2 number 25 bars at the left support up to 1.5 meters from the support face. For the purpose of placement of stirrups, extend two number 25 bars at the left support all the way to the end point of the number 32 bars. And so this is what we have done in the example. So we have four number 32. They are extended 2 meters. There are four number 25. Two of them are extended 1.5 meters. The other two are continued, and here they are lapped with the number 32 bars. And the 1.5 meters and 2 meters are based on the extensions beyond the inflection point. So we need extension of 482 from the inflection points, and the inflection points are at 1 meter and 1.5 meters. So we so we could go 1 meter plus the extension, and here we could go 1.5 meters plus the extension, and that's precisely what has been done. These bars have been extended to 1.5 meters, and those bars have been extended to 2 meters, 1.5 meter to inflection point plus half a meter beyond the inflection point. So this is the we talked about the bottom bars before, the top bars. This is the final solution, and I think the whole thing makes sense. Because of time pressure, I feel that I may not have done the best job, at least in places, but if you did the example on your own, I think you will see that it's a pretty sound, well done example that illustrates the various things that we have discussed. Now this is almost 3 hours. Let me consult with both. The other two examples are shorter. Should we lump them with the question and answer session on Monday?
Next Monday, you're saying?
Next Monday is when I'm talking about.
We
That's
can.
when I'll do two-way slabs for flexion.
Okay. Yeah, we can do that.
Or
Right now it is 10:54, so you just have 6 minutes. So I don't think you can cover both the examples in 6 minutes. That will be.
I can cover, but it will probably not be the best. Yeah.
Right.
Let us postpone. Yeah. I think we probably have gotten to our limit today. Yeah, I'm sorry about the amount of material, but I put it in because I thought it was necessary, as you would imagine. So, okay, I think we will conclude here. Are there lots of questions that are unanswered?
No, most of the questions we answered actually, me and Dr. Akib.
Okay. Okay.
Yeah, so a few of them, if they are not answered, then I will save the question answers, so we
Okay.
can talk about it.
Since it is Monday, actually, come to think of it, I will start with these two examples and answer a few questions. That shouldn't be more than a half hour, and then I'm sure we still be, because I have made a decision about the flexural design that will save us time. So we should be okay.
Okay.
Yeah.
So tomorrow we have one more lecture, right? On concrete.
Yes.
And yeah, so
yeah, I wouldn't carry this over to tomorrow, because tomorrow we will not have time. Tomorrow we will talk about columns. It will be a full lecture, but we shouldn't have time problems. I will go up to 10:30 and then answer questions from 10:30 to 11, the usual. Only today I kind of sensed from the beginning that would be a problem.
right. Okay, Dr. Ghosh. So
Yeah.
thank you for your lecture today. It was it was really good, and this is a very important topic actually because
Yeah.
uh, lab splicing and like development length, these topics are not easily understood, even for practicing engineers. So thank you for covering this topic today, and thank you to all the participants for joining in and like in big numbers once again. And yeah, like we couldn't get to all of your questions probably, but most of them we have answered actually. So
Mhm.
both me and Dr. gave most of them. I think 90% of them have been answered. So
Great, great,
I don't
great.
think there are a lot left. Uh, so yeah, so see you tomorrow, and
Yeah.
hope you have a good day.
Yeah.
I
Tomorrow
will.
columns,
Yeah.
tomorrow columns, and I shouldn't have time problem, I can assure you. Yeah.
Okay. Yeah.
Okay.
Yeah. I will open up the quiz in a couple of minutes.
Thank you.
Thank you.